Humanity's journey has always been one of expansion, from the cradle of Africa across continents to the vastness of the oceans. But our greatest migration is yet to come. We stand on the precipice of becoming a truly cosmic species, a future where our destiny is not bound by a single planet, but written in the stars. This is the story of the infinite migration, the epic saga of humanity's ascent into the final frontier. Join us as we explore the challenges, the wonders, and the ultimate fate of humankind among the cosmos. The dawn of interstellar travel. The nascent stages of interstellar travel are marked by monumental leaps in propulsion technology and a redefinition of humanity's place in the cosmos. As we stand on the precipice of venturing beyond our solar cradle, the dream of reaching distant stars is slowly transitioning from science fiction to engineering reality. This endeavor hinges on overcoming the immense distances involved, distances that render conventional rocket propulsion woefully inadequate. Current projections and theoretical frameworks point towards revolutionary concepts such as fusion drives, antimatter engines, and perhaps even more exotic methods like warp drives or alcubiometrics, which propose manipulating spacetime itself to achieve faster-than-light travel. These technologies, while still largely in their theoretical or early experimental phases, represent the critical breakthroughs needed to make interstellar journeys feasible within human lifespans. The sheer scale of interstellar distances necessitates a paradigm shift in how we conceive of spaceflight. A journey to Proxima Centauri, the nearest star system to our own, would take tens of thousands of years with current spacecraft speeds. To achieve this, scientists are exploring advanced propulsion systems. Fusion rockets, harnessing the immense energy released by nuclear fusion, could offer significantly higher exhaust velocities than chemical rockets, drastically reducing travel times. Antimatter propulsion, while posing considerable technological and safety challenges, promises the highest energy density of any known fuel source, potentially enabling speeds that approach a significant fraction of the speed of light. Research into these areas is not merely academic. It is a crucial step in ensuring humanity's long-term survival and expansion. Beyond propulsion, the challenges of interstellar travel extend to life support, navigation, and the very architecture of starships. Vessels designed for voyages spanning decades or centuries must be self-sustaining ecosystems, capable of recycling air, water, and waste with near-perfect efficiency. Advanced AI will be essential for autonomous navigation, system maintenance, and managing the complex operations of a starship far from any terrestrial support. Furthermore, the psychological and physiological effects of prolonged deep space travel on human crews are significant considerations, potentially necessitating innovations in artificial gravity, radiation shielding, and even suspended animation or biological augmentation. The development of these multifaceted technologies underscores the profound commitment required to become a truly interstellar species. Challenges of long-duration spaceflight. The human body, a marvel of biological engineering, is ill-suited for extended periods beyond Earth's protective embrace. Bone density plummets, with astronauts losing up to 1–2% of bone mass per month in microgravity, a rate that would lead to severe osteoporosis within years. Muscles atrophy due to lack of use, diminishing strength and endurance. The cardiovascular system, no longer fighting gravity, becomes less efficient, leading to orthostatic intolerance upon return to a gravity environment. Radiation exposure is another significant hurdle. Outside Earth's magnetosphere, cosmic rays and solar particle events bombard spacecraft, increasing cancer risk and potentially causing central nervous system damage. Shielding can mitigate some of this, but a truly deep space mission would require novel solutions, perhaps even biological adaptations or artificial magnetospheres. Psychological well-being faces immense strain. Confinement in small, artificial environments for years, far from loved ones and familiar surroundings, can trigger anxiety, depression, and interpersonal conflicts. The sheer monotony of life aboard a spacecraft, punctuated only by routine tasks and the occasional awe-inspiring vista, takes a toll. Maintaining crew cohesion and mental health requires rigorous psychological screening, robust support systems, and carefully designed habitats that offer privacy and opportunities for recreation. Communication delays with Earth, which can range from minutes to hours depending on distance, further exacerbate feelings of isolation and complicate emergency response. Nutritional and medical challenges are equally daunting. Producing fresh food in sufficient quantities for multi-year voyages is a complex logistical puzzle, often relying on processed or dried rations that can lead to nutrient deficiencies and monotony. Medical emergencies pose a critical threat. A serious illness or injury far from Earth could be fatal without advanced onboard medical facilities and trained personnel capable of performing complex procedures. Developing reliable, long-term life support systems that recycle air, water, and waste with near-perfect efficiency is paramount. Any failure in these closed-loop systems could have catastrophic consequences for the crew. The sheer scale of resources required for a long-duration mission is staggering. Launching massive amounts of supplies, equipment, and fuel into orbit is prohibitively expensive. This necessitates a paradigm shift towards in-situ resource utilization, harnessing materials found on celestial bodies like the Moon or Mars for fuel, water, and construction. Furthermore, the technological reliability required for systems operating autonomously for decades is unprecedented. Redundancy is key, but even the most robust systems can fail, demanding innovative solutions for repair and maintenance in a hostile environment where spare parts may be a finite commodity. Establishing extraterrestrial colonies. The establishment of extraterrestrial colonies represents humanity's next great leap, a necessary step for long-term survival and expansion. Such endeavors demand meticulous planning, advanced technology, and a profound understanding of the environments we aim to inhabit. Initial colonization efforts will likely focus on locations within our solar system that offer the most accessible resources and manageable conditions. Mars, with its thin atmosphere, presence of water ice, and relative proximity, remains a prime candidate. Establishing a self-sustaining base there would involve in-situ resource utilization, such as extracting water for life support and fuel, and cultivating crops in controlled environments. Beyond Mars, the moons of Jupiter and Saturn, like Europa and Titan, present intriguing, albeit more challenging, possibilities. Europa's subsurface ocean could harbor life and offer a source of water, though its extreme radiation environment necessitates heavily shielded habitats. Titan, with its dense atmosphere and liquid methane lakes, offers a unique setting for specialized exploration and potential resource extraction, though human habitation would require entirely novel technological solutions for survival in its frigid temperatures and alien chemistry. These missions would not only expand our physical reach, but also drive innovation in areas like closed-loop life support systems, advanced propulsion, and radiation shielding. The transition from temporary outposts to permanent, self-sufficient colonies involves overcoming significant hurdles. Developing robust infrastructure, including power generation, manufacturing capabilities, and waste recycling, is paramount. Terraforming, the process of modifying a planet's atmosphere, temperature, surface topography, and ecology to be similar to the environment of Earth, may be a long-term goal for some celestial bodies, though it presents immense ethical and technological challenges. Genetic engineering and cybernetic augmentation might also become crucial for adapting to alien environments, ensuring the long-term viability of human populations far from Earth. Ultimately, the success of extraterrestrial colonization hinges on our ability to adapt and innovate. It requires a global commitment, fostering international cooperation and pooling resources to tackle the monumental tasks ahead. The creation of diverse, resilient off-world communities will redefine what it means to be human, scattering our species across the cosmos and ensuring our enduring presence among the stars. This expansion is not merely about finding new homes. It is about securing a future where humanity is no longer confined to a single, vulnerable cradle. Human evolution in new environments. The vastness of space presents environments unlike anything on Earth. As humanity expands to new worlds, our biology will inevitably adapt. Consider the challenges of lower gravity on Mars or the Moon. Over generations, this could lead to taller, more slender physiques with decreased bone density, a phenomenon already observed in astronauts during extended space flights. Muscle mass would also likely decrease without the constant resistance of Earth's gravity. On planets with different atmospheric compositions or higher radiation levels, evolutionary pressures would drive significant changes. Perhaps a thicker epidermis or enhanced melanin production would become common to shield against stellar radiation. Respiratory systems might evolve to process thinner or more exotic atmospheres, potentially with larger lung capacities or more efficient oxygen-binding proteins in the blood. Sensory organs could also adapt. Eyes might evolve to perceive different light spectrums prevalent in alien skies, or other senses might become more acute to navigate environments with limited visibility. Furthermore, the psychological and social structures of humanity will be reshaped by the frontier. Isolation and the need for extreme cooperation could foster new forms of communal living and decision-making. The very definition of human might blur as cybernetic enhancements become commonplace, necessary for survival in hostile alien conditions. These integrated technologies could augment our senses, provide direct neural interfaces with ship systems, or even offer forms of digital consciousness. The line between organic and artificial will continue to dissolve, creating beings uniquely suited to their chosen cosmic niche. The long-term journey between star systems, whether through generation ships or suspended animation, imposes its own evolutionary timeline. Genetic drift and the isolation of populations on separate vessels could lead to divergence over millennia. Each ship, a self-contained arc, would become a crucible for distinct evolutionary paths. Such journeys might even necessitate deliberate genetic modifications to ensure the long-term viability of the species, tailoring future generations for specific exoplanetary conditions before arrival. The ethics of terraforming and xenogenesis. Terraforming alien worlds presents a profound ethical quandary. Should humanity have the right to fundamentally alter a planet's biosphere to suit our needs, potentially eradicating any indigenous microbial life or even complex ecosystems that may have arisen independently? The Prime Directive in Star Trek, while fictional, highlights this dilemma: the non-interference with the natural development of alien civilizations and environments. Applying this principle to nascent or even established alien biospheres suggests a moral imperative to observe and study, rather than to dominate and reshape. Consider the potential for unforeseen ecological collapse if we introduce Earth-based life or alter atmospheric compositions without a complete understanding of the alien planet's delicate balance. The very act of terraforming implies a belief in human exceptionalism, a notion that our form of life is inherently superior or more deserving of planetary habitation. This anthropocentric view risks repeating historical patterns of colonization and exploitation, albeit on a cosmic scale. Xenogenesis, the creation of alien life forms, adds another layer of complexity. If we engineer life to survive on a terraformed world, are we playing God? What responsibilities do we have to these synthetic life forms? Do they possess rights? The potential for unintended consequences is immense. Creating organisms that could outcompete native life, or even evolve in unpredictable ways that pose a threat to human colonists, is a significant risk. Furthermore, the very act of designing life raises questions about the definition of life itself and our role in its perpetuation or creation. It forces us to confront our own biological limitations and the hubris that might accompany such endeavors. The ethical framework for developing and deploying xenogenetic organisms must be as robust as that for terraforming, if not more so, given the direct manipulation of biological processes. The question of whether a planet is dead or alive is also fraught with ethical ambiguity. Current scientific understanding often defines life by its biochemical processes, but what if alien life exists in forms we don't readily recognize? Microbial life, for instance, might be present in subsurface oceans or within the planet's crust, undetectable by our current methods. Eradicating such life, even unintentionally, through terraforming processes would be a catastrophic loss of unique biological heritage. The scientific and philosophical value of discovering independent abiogenesis, life arising from non-living matter, on another world cannot be overstated. To destroy such a discovery before it is fully understood, for the sake of human expansion, would be an act of unparalleled cosmic vandalism. Ultimately, the ethics of terraforming and xenogenesis demand a cautious, humble, and deeply considered approach. It requires a shift from a paradigm of conquest and control to one of stewardship and respect. If humanity is to become a truly spacefaring civilization, our expansion must be guided by principles that acknowledge the intrinsic value of all life, regardless of its origin or form. This means prioritizing observation, non-interference, and the preservation of unique alien biospheres above the immediate convenience of human colonization. Developing robust ethical guidelines and international, or even interplanetary, consensus on these issues is paramount before we irrevocably alter worlds beyond our own. The Fermi paradox and our place in the cosmos. The vastness of the universe presents a profound question. If the conditions for life are common and stars teem with planets, where is everybody? This is the essence of the Fermi paradox, a stark contradiction between the high probability of extraterrestrial civilizations and the utter lack of evidence for them. Our galaxy alone contains hundreds of billions of stars, and statistically, many of these stars should host planets within their habitable zones. Given billions of years of cosmic history, it seems logical that at least some of these planets would have developed intelligent life, and some of those civilizations would have advanced to a stage where interstellar communication or travel is possible. Yet, the silence from the cosmos is deafening. Several hypotheses attempt to resolve this paradox. Perhaps intelligent life is exceedingly rare, a cosmic accident confined to Earth. Or maybe civilizations, upon reaching a certain technological threshold, invariably self-destruct through war, environmental collapse, or uncontrolled artificial intelligence. Another possibility is that advanced civilizations choose to remain hidden, perhaps adhering to a non-interference policy with less developed species, or existing in forms we cannot comprehend or detect, such as digital consciousnesses or beings operating in dimensions beyond our perception. The Great Filter theory suggests there's a barrier so difficult to overcome that few, if any, species make it through to becoming an interstellar civilization. This filter could be in our past, meaning we've already overcome a great hurdle, or it could be in our future, a daunting challenge we have yet to face. Our place in the cosmos, viewed through the lens of the Fermi paradox, is one of profound uncertainty and potential isolation. If we are truly alone, the responsibility for the continuation of consciousness and intelligence falls solely upon humanity. This imbues our existence with immense significance, but also with a heavy burden. Conversely, if civilizations do exist but are undetectable, it implies limitations in our current scientific understanding and technological capabilities. We may be like an ant colony on a busy highway, unaware of the vehicles that rush past. The search for extraterrestrial intelligence, SETI, continues, scanning the skies for signals, but the paradox remains a powerful reminder of our cosmic solitude or our limited perspective. The implications of the Fermi paradox extend beyond mere curiosity. They touch upon our understanding of life's origins, the trajectory of civilizations, and humanity's ultimate destiny. If we are alone, the imperative to explore, expand, and safeguard our species becomes paramount. If we are not alone, but simply haven't found others, it suggests that the challenges of interstellar communication and travel are far greater than we imagine, or that the nature of advanced intelligence is fundamentally alien to our current concepts. The paradox compels us to confront our assumptions about life and intelligence, pushing the boundaries of scientific inquiry and philosophical contemplation as we continue to gaze at the stars and ponder our unique, or perhaps not so unique, existence. As we stand on the precipice of a new cosmic era, the journey of humanity into the vast unknown has just begun. We've explored the potential futures, the challenges, and the sheer boundless possibility of becoming a truly spacefaring civilization. This isn't just a dream. It's our destiny, waiting to be written among the stars. What will our first interstellar colonies look like? Join us next time as we delve into the architectural marvels and societal structures of humanity's first off-world settlements.